Okay, so let's pick up where we were. So where we ended last time is I kind of rushed at the end through some definition of contractibility and then used that as the base case for defining the n-type. So let me mention a couple of things about contractibility. So this is, is contractible. So the terminology is contractible, and I just want to point out something about this. So we define that to be that there is a point in A such that for every other point in A is equal to it. Okay? So this is just our definition of what contractibility is, this notion of contractible. So as I depicted on the board last time, it says that there's a point here, which is this so-called center of contraction, or we'll just call it the center of A, such that if you have any other points anywhere else in the space, that they are sort of equal to it. So in a way, it looks, one can think of it as that picture makes it look kind of star-shaped or something, because everything else around it is equal to it. And then you can kind of think of moving these along those edges, just doing identifications. If those are proofs of identity, then these are identifications, and so we can think of contracting the thing to a point. So that's the notion of contractibility. The other way to think about it is you could also think of it as expressing, and we're going to use this, is it expresses in isolation, if you would like to say it like that, expresses the idea of unique existence. In isolation, because if you think of it like this, for example, we're going to discuss an instance of this shortly, but the idea is it says there exists something in A such that every other thing in A is equal to it. So it's expressing, you can think of it as expressing just the package of what you think, what you say when you say, typically it's in a context where you say, well, for every blah, 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 there exists a unique, well, that will come out as is contractible. Okay, and that's going to be related to a definition I'm going to give in a little while about that. So we can think of it as expresses unique existence. And I don't really want to write a notation for it, but on the board we often write, exists unique. Okay, so this would be exists unique A, roughly. It might look something like that. But if you want to emphasize that it's kind of constructive existence that I actually give it, then it might look like something like that. But anyway, I'm not really suggesting. I'm just reminding you that, so people often write things like that, exists, some X in here. So that's what this is, what this is expressing. Of course, well, let me just stop there. I just want to mention that as a point. Okay, so that's the first thing. And then we mentioned a couple of other things, is that we can easily show that being contractible is equivalent to, right, this is equivalent to, the following things are equivalent if and only if we can say A is equivalent to 1. Okay, so the idea is pretty clear just from the pictures, I won't write out everything, that what we're really saying is if we say that the type is contractible, you're saying it's tantamount to a singleton, because there's a point in there, maybe there's, maybe there's a distinguished point in here, we distinguish one point that everything else is equal to. So effectively it's a singleton, okay? And then we can also say, you can also express this as saying what I wanted to say, is that the simple thing, which I call, is prop of A, it's a prop, okay, that it has at most one point and it's inhabited. That's another way of saying it, okay? So this is all the same thing, is inhabited, where this obviously means there exists an X in A such that 1, and this we defined earlier, which says there's at most one thing. And that's kind of clear, right? Because I'm saying it's inhabited, and it has at most one element. Well, actually, since it's inhabited, it has exactly one element. And so that's what's being said here. So that's another way to think about what contractibility is. And then an example that's in the book that we actually used implicitly when we were talking about the justification for J is the contractibility of this type, that the partial path space, if you want to say that, the X is in A such that A is equal to X, for given A in A. Okay, so this can be thought of as the half of the identity type, if you like. We can say that this is contractible. In other words, if you fix any point you feel like in A, all right, well, it's not necessarily, who knows? There could be many disconnected other things around, but you can consider the local, using this loosely, the neighborhood of A in some way. You could consider the things that are all reachable from A, and I'll group them in this little area here for no good reason, just for pictorial reasons. And so we can think of that as the things that are equal to A. So it's sort of like, sometimes I like to think of this as the star of A, right? It's sort of the asterisks that is centered at A, and if the space is contractible and A is a center of contraction, then it would be the whole of A, but it's not necessarily the whole of A. So we can look at that, and that's contractible, and so the question is, what is the center? And this is the kind of thing we used before. Well, what would the center of contraction of the sum of all these things, so basically the subspace here, the sum, now remember, has more structure. So this picture is a little misleading because I'm not really depicting the sum. I was looking at the part of A that is reachable from little a. But if you look at the sum type, right, then the sum is kind of collecting up, right, all of the x's that have this property, but in a proof-relevant way. So these are the x's that are equal to A. So what would its center of contraction be? Well, the thing that everything else, if you think about it for a moment, it's going to be A and reflexivity in A at A, okay? Because remember, there's the dependency. So once I choose x to be A, then this becomes A equals A, okay? And now, if I took any other element of this type, let's call it B and P, the claim is that these are equal, right? That A ref of A is equal to B and P, provided that B is in here, because we're claiming the contractibility of this sum type. And that's so sorry for where my equal sign is. Equal sign, this is equal to that. Okay, got hanging out there. So we need to show for any such B and P. And so then you do this exact same move that we did in the justification, so I won't repeat it here. So I'll say CF, my discussion of the justification of J, and you'll say, oh yes, I've seen that argument before, because I gave it there, and so it can be expressed here. And I think we're gonna need this remark a little bit later, so I thought I would mention it. So it's sort of catching up loose ends here. Okay, so that's the notion of contractibility. And then, as I said to you, I won't repeat the definition here, you can then build up, sorry, I'm paging through my notes, figure out where I am. You can then build up from there the hierarchy of n types, starting with n being -2 and building up building up by just saying that an n+1 type is one whose equality type, every possible equality type is an n type. Okay, so that's what we do. So we build that up. Okay, so that's a little bit I wanted to say about contractibility. The role of this remark will become apparent in a moment, but I want to now talk about propositions and truncation again in a little more detail, and then I will come back to the propositional truncation. Then I will come back to why I wanted to bring that up in a second. Okay, so now the thing we talked about last time, and I kind of got most of the way through it, and I forgot to put in a few points that I intended to make, but I got lost in the general discussion, and so let me just make sure I write down the rules. So this will be what is called the special case of the propositional truncation, which is also known as the -1 truncation, because once you have that numbering, then the way it works out is propositional in the technical sense of the word propositional. Propositional corresponds to the homotopy level -1, so it's also called the -1 truncation. So we mentioned that we have, the way I wrote it was here, if we sometimes will write it sub -1, or if that's obvious in the context, as it will be for today's discussion, I'll just write it like that. So that's what we did. So this is going to be a type, so that'll be the -1 truncation. You can obviously say that, see that what's going to happen is I'm going to have a generalization of this, which is called the n truncation. And in fact, we'll find it useful to talk about the 0 truncation, which constrains something to being a set, constrains a type to being a type to be a set. So the idea, and this is what I didn't finish writing out last time, is that, of course, I want the -1 truncation. Well, let me write it in the notation I've been using. I want the -1 truncation to A for any A. I don't care, let's just write in U, but for any type. So I want that to be a proposition. So what does it mean to be a proposition? Remember, it means that it has at most one proof, or another way of saying it is, yes, at most one element, which is another way of saying it is. So this can be said as, remember we worked out equivalence. This says that for every x, y in, well, in this case it's A. What we're saying is that the equality type is contractible. So in other words, remember now on the left-hand board what contractible says. So contractability has this positive aspect to it. There exists an element of that. So I'm telling you x is equal to y because it's inhabited, and moreover there's at most one element of that. Okay, and that so that's the idea. So we're saying that's what is being. That's another way of saying what if you crank out what is -1, if you're using that hierarchy I described, then this is what you'll get. Okay, so so the idea is I want to guarantee that any two elements are going to be equal. So what we did is with the introduction rule, and let me try to write it out more carefully now. We said, well, so the intuition, of course, is that the propositional truncation expresses what is sometimes called the mere inhabitation of A. So when last year we were sort of working out what to call things, we eventually settled, I sort of had the feeling we all kind of settled on this, but nobody really loved it. But we decided to call it the mere inhabitation. So the problem is this, is that there's a terminological confusion, and it particularly comes up in connection with existence, which I'm going to talk about actually in a moment. But the idea is that in a constructive setting, when you say that something exists, it means you must exhibit it. So that's the idea of existence. But if you want to express the weaker notion of existence that you find in classical logic, then we decided to call that mere existence. Okay, I don't know that I loved that word, but I certainly don't have a better suggestion. So there was not a, so that was like, it's now become our convention. I'm just introducing the convention. So this is expressing more generically the mere inhabitation, meaning that if you have, well, here I'm going to witness the mere inhabitation of A by saying any element of A can count as a witness of it being merely inhabited. So the merely part comes in the elim rule, which I explained last time, but I'm going to repeat them here, where you want to say that I want to prevent clients, I like to think in a CS way, I want to prevent clients from depending on what was the witness. Okay, that's what I want to do. Okay, so that's what the mere part is going to be. So that you have a weaker, if you want to express something weaker like mere existence, you can't reason from the fact that it exists and care what it is. You have to somehow be oblivious to what it is, and so we have a way of doing that. But before we get there, the thing that I didn't spell out properly last time, so I'll do it now, is, well, the brute fact that we have to stipulate that what we get is a proposition. Obviously, that was the whole idea. That's why it's called propositional truncation. So, so I need to state that what I have is a proposition. So the way you can say this is that you demand, one way to do it is, you demand for any two elements of the so-called truncated type, all right, written like that, I'm going to need a witness. I wasn't quite sure what to call it. I could call it, squash of xy. Okay, is a proof that x is equal in that type to y. Okay, so I'm really just saying I'm specifying every two elements, I'm specifying directly the idea that any two elements of the truncated type are in fact equal by postulating a witness to this fact written here. Now, a little later, this will turn out to be an instance of something that amounts to a kind of quotient construct, and we'll come to that a little bit later. But right now, this is a primitive notion. So I have to have this kind of constructor, and then this will bring up an issue about the eliminator that I didn't get to either. So let me mention that as well. So the eliminator, we just, after a little bit of discussion last time, we said, well, suppose we have an element of the squash or the truncation of A. This is all the -1 truncation, and I want to reason from that fact. Well, it seems perfectly reasonable to say, well, you're telling me A is inhabited, so let X be the inhabitant, okay? And I will work on that basis and compute some B, and then I'll leave a little space. Then I want to have, well, who knows what to call this? Elim something, so we'll write this B. Okay, this is again a special case of a more general rule. I'll leave some space, and this will be B. So that's where we got to last time. And then after some discussion, we said, well, the rule that is given in the hot book is that I want the following. I want you to prove to me, give me a proof P, that B is a proposition. And then that proof would actually go in here as well. And then what I didn't get to was talking about the definitional equivalences, so I'll mention that in a second. Okay, so the intuition we developed last time, which I think is now ready, everyone understands, is this is by demanding that B be a proposition, I'm ensuring that N's outcome cannot possibly depend on which representative I chose to witness the inhabitation of A, because there's only at most one thing in B, and N is one thing, and any other thing will be equal to that thing. So up to higher homotopy, you will get the same result. But the trick is you have to be careful. All these little slippery words when I just say is or the same, or you got to be careful, because the equality means equality in the theory, which has this structure of identifications, right, that we talked about. So this is what this is expressing, what is being expressed here. And so you could guess, and you would be right, that the way you would do like the zero truncation is you demand that the outcome be a set. Okay, so that you only know the setness, okay, the set aspects of type A. So the zero truncation, here, this is the -1, if I wanted to write it there. But if I were doing the set truncation, then what I want to say is, well, I'm allowed to consider multiple elements, but there should be at most one way to consider them equal. That's what it is to be a set. So I want the guy that depends on this because of functoriality. N is functorial in the paths that are in A, and I want to make sure it respects that propositional nature of the path type associated with a set. That would be the zero truncation. And so we want to demand that, and we're going to demand that. One way to demand that is to say that itself be a set. So that's the idea, because it would take paths to paths, right? That's the apply to paths aspect of things. And the apply to path would give you, if you gave me two paths here, would give me two paths over here. And if I demand that there can be at most one by saying it has to be a set, then I have demanded that it be well defined with respect to those paths. So that would be what one would do. Okay, and it's also true that one can do a dependent version of this, but I won't need it for today, so I won't write it down. Now, the definitional equivalences come up again, and these are the same issue that we've had before, because this is another instance, as was the interval when I did the interval axiomatically. It's another instance of a scenario in which I am postulating a path or an identification that doesn't arise, just from the pure structure of equality, but is stuck in here. That says we have a squash which witnesses their equality. And that happened with univalence, which said that any equivalence can be turned into a path. And it happened with the interval in which I just postulated a path called the segment. So here's another one. It's a parametrized family of paths, squash of x, y. So we're going to get the exact same issues that we had with those other ones, which are the following. It seems by Genson's inversion principle, we would say if you're eliminating with, bar m and you have x dot n and you have p, then you would expect on the basis of the inversion principle that to be m for xn, and this would be taking place in B. Okay, we're writing like that. So you could expect that. So this one seems plausible and reasonable. And then we have that exact same problem which I mentioned with the interval. Because you would like to say something about what do I do when I do apply to path, right? If I do an apply to path of something, of particularly this elim form, so I would like to say, I have to way of writing this, lambda z or something, elim. I want to express the functoriality of this guy, and I want to do an apply to path, right? So I want to think of that as a function of that position and apply it to a path. And that's what that is saying is I want to say something about, I would like this to be somehow to be, if applied to, squash, of, let's say, what should I do here? P is prop, so let's just write it as, I need names for the endpoints, R and S, I don't know, squash of R and S. We would like that to be equal to, well, the proof P that something is a proposition and instantiated in which I put in R, or applied to R and S, right? Because remember, is prop is pi xy, okay? So we've written like here, and so we want to do that. Or maybe I have to write, these are squash, I've got it written that, no, that's all right, that at least makes type sense. Okay, so we can write it like that. And of course, this is problematic. This is the same issue we had with the elim form on the segment, on the interval. When applied to the segment, you would think, you would like to say something about how it behaves, and this doesn't come out for free, as far as I know. So I'll mark this as a question mark, right? This is like question mark, okay? The action on paths is maybe a little unclear, okay? Another way of saying it is, it comes down to the same thing if you work it out, is if you're doing a J and the argument is a squash, it's really going to amount to the same thing. And if I do a squash RS, so where is this? This is an inhabitant of R equals in the truncation of AS, okay, and I then have my X dot, whatever I called it, N, okay, which was the typical thing for J, and I have the motive, which I typically write here, okay. The question is, what should that be definitionally equal to? Because the action on path is defined in terms of J. So you'll have to remember when you go back and look at it. So if you unravel it, really the issue is poor J doesn't know what to do on squash because nobody ever told it what to do on squash. All it ever knows what to do about is instances of reflexivity. Okay, so from a computational point of view, it's stuck. So this and this are like kind of amounting to the same thing because the action on paths for some function takes this guy and does a J on it, okay, and then actually it yields the identity type, okay, because of the reduction to reflexivity. Yeah.
Aren't R and S of type like brackets?
The witnesses, yeah, they're bracket type here.
Yeah, but then doesn't P take just plain like? Doesn't P take just plain things of like type B?
No, P is prop. Oh, is prop. Oh, yeah. So this is what I made a mistake. I hesitated there, for a second, and I knew that wasn't right. Yes, you're quite right. So that is not quite what I wanted to say. Okay. So what is it that I wanted to say? Yeah, that's correct. That is not what I wanted to say exactly, because this is B is prop. Okay, so I wanted to say this is the witness. This is going. What I want to do is to come up with the witness. I want to come up with the witness. Okay, what I need is the witness that. Okay, N. Well, let's write it as R for S. No, it can't be that either. Well, all right. Let me think of this. I want to look at the witness of well-definedness of N. So now I'm not going to be able to do this at the board in front of you. So the witness to the well-definedness of N. Okay, that's what I'm looking for. Okay, and that's the thing that I need to. Yeah. So let me figure out later what to write there. All right, I'll put it on the piazza. You're right. It's not that. The thing I wanted to focus on is that apply to path amounts to a J, and so because it amounts to a J, because this is a given notion, okay, then it'll do a J on a squash, and when it does a J on a squash, there's no definitional equation that applies to that, okay, and so that is tells us that probably, I don't know what it tells us exactly, but it's related to the mysteries a little bit about how to think of this computationally. So remember, we motivated this by saying we're applying Gensen's inversion principle, which is kind of the beta principles. This is for 0 cells, and this, you ought to have a similar one for 1 cell, because if I think of this, you can think of this as, if you think of this as like the 1 application, then this would be the 0 application of that same elim, okay, to M. Yeah, so probably what I need to do here is state the axiom in terms of something in the image of M of the bars bar M and bar N, and then I can get it to work probably. But let me not try to solve that at the board because I'll screw it up worse. Okay, so you can think of this as like the 0 cell application to M, and it has a defining equation that's a beta-like equation here, which is we wrote there. And so the analogy that we were thinking of, well, then the 1 application of something, okay, of that same elim thing to a path in that space should also have some kind of, so maybe I should restrict this to bar M and bar N to get it to look like a beta redex. That's what I want to get at, okay. And then I'll need that, okay, so that's what we'll do here. But it's going to be the same issue in any case, because you kind of feel like that ought to hold for the exact, you feel like it's for the exact same reason, because the elim as a function of this position has a functorial, is 2 parts, you could say. It acts on the 0 cells, it acts on the points, and it also acts on the paths. And here's the path. But the way things are defined, it doesn't do a reduction, even though I didn't write the right thing here, but something involving P will get written in here, and that will make that work.
I think last time when you wrote the second rule over there, you wrote it in terms of like X of type A and Y of type A, and then you just said like you have the identity of the squash.
Yeah, of the squash. But I want to really say, so the thing that I really want to say is that everything in X in bars A is equal to each other. That way it's very blatantly obvious that it's a proposition. Okay. So that's the idea. In other words, I forcibly, so this is the part that makes it come true that this is a proposition. And it does it in a completely non-subtle way. It just says blat. It just imposes it. Okay, so that's the idea. Okay, so let me owe you what I'm supposed to write there, but you can probably figure it out, or note takers can figure it out. But anyway, I just wanted to point out, it's the same issue, okay, that we have seen before, is that if we kind of follow our nose with type theoretic instincts, we're sort of led to expect on the basis of Gensen's principles these kind of beta equations, and these tend to hold, although we're going to see next week a situation when even this doesn't work out very well in the hot setting. So all these things are somewhat questionable at the moment. We don't know. Okay, but if you, insofar as you accept that this ought to be the case, you're certainly tempted at the very least to say that something like this ought to be the case. There needs to be some way of having it act on the this specified path. Okay, so the same thing happened with the interval that we wrote. Okay, so good. That's good. That's what I wanted to say about that. Now I want to say something about using the truncation. So that's what I want to do next. Okay, so let me just find where I am. Okay, good. All right. So we're good with that? Okay, so now what I want to do is I want to revisit, this is also in the book if you want to look at it. So I'll revisit what is called the axiom of choice. Let me just write it like that. The so-called axiom of choice. So we talked about this before, and I'm now able to talk about it a little bit more meaningfully. So first of all, let's remember what we talked about before. So we wrote down a principle, which I will now call AC infinity. Okay, which says for any type, so I could really write it out as, it gets a little heavy, but let me write it out once just so we can see this. For any types A and any family of types B, so this is quantified like that. So the AC infinity part says I'm making no restriction on A and B. These are arbitrary types. That's the idea of writing it arrow U here. These are arbitrary types. And if this were universe polymorphic, then that would be, a floating I level you want. So by writing constraining it to U, I'm not trying to say it has to be somehow a small type. I'm just saying it's any type, and this is universe polymorphic. So whatever level you're at of the universe hierarchy, this will apply. So that's what is meant here. So there's no significant restriction on A and B. And then what we said was the expression of the axiom of choice was saying if you have a total O in every R, I might have called it R or C, I don't remember, C, okay, which in the full generality is pi x in A, B arrow U. So, or if you like, you can think of this as sigma x in A, B arrow U, that's the same thing. Either way, well, up to minor differences. That's the same thing, that's an equivalent type. So in other words, given a relation between A and B, but it's a dependent relation. That is, the type of the second argument depends on the choice of the first argument. If it's a total relation, so if for every x in A, there exists constructively a y in B, and remember this depends on x, so I could emphasize that. If it's the case, this is what we said before, if that is the case, so I'll put this part in brackets, then, because it's inside the quantifier here, okay, these string of quantifiers here, okay, then what? Well, then there's a choice function, okay, so there is an f, and what will the f be? It will, well, from A to B, but it's from pi x in A, B, okay, written like that, which, what does it do? It says if you tell me which domain element you're interested in, I will give you a witness to the fact that C holds, I call it F, yeah, that C holds on that, for that particular witness. I will pick out a witness that tells you that if C is total, then I will pick out a witness of the totality, okay? Okay, so that's what we did. And you can check, in fact, that this is, in fact, an equivalence. That is, if we can write, I'll just write it like that, that this is, so that, that this is an equivalence. It's a definable equivalence. You can write this thing down. It's a definable equivalence. In other words, what I want to say is this. It's not an axiom, it's a theorem. That is, it's the theorem of choice, okay? In other words, what we have is the theorem of choice, okay? Nobody outside of this room would ever say that, but in this setting, we're almost, in a type theoretic setting, it's the theorem of choice, okay? All right, because I mentioned to you before, in type theory, this is a theorem. And why? Let's think about what equivalence we're talking about. So let's write it down just so we can see. So going from left to right, right? So we're going to take in lambda, let's call it capital F, which is the witness of the totality, okay? And now I got to emit something in here, right? So what do? I want to emit a pair, okay? And I want a function from pi x in AB, so it'll be lambda x, that's my x in A, and I want something in B of x. Well, where do I get that? Well, I apply f to that x and take the first component. So first of f of x, okay? And if I want, now the other component of the pair says this, I want an element of this function space, lambda x here. But remember, I want this to hold for that, given that choice of f, okay? In other words, the f, it's dependent. So the f I choose goes in, and then we want an element where f is that guy, okay? And if you work that out, it's just second of f of x. Okay, where we define the sigma negatively by projections first and second. So we can write it like that. So that's the sort of left to right direction. And the right to left direction is similar. If you'll allow me to write some more intuitive notation, give me f, and give me a pair f, and give me, let's call that g, because I'm not imaginative. Okay, now I want to emit one of these. So it's a lambda x, right? And now I need to get a pair. So how do I get a bx out of what I've got? Well, f is pi x in AB, so I can do fx, okay? And then I want to get something in C of x with that choice of y, namely fx, and so that should turn out to be gx, if I'm not mistaken. I'm doing this off the top of my head. I should know better than do that. I think it's just gx will work because g is going to be one of these guys, and if you apply it to x, we'll give you a witness for the choice you made here, and that should be what I need here. Okay, that should work. Yep, because the choice I made here was literally fx. So I'm pretty sure that's right. I like to work at the board like with you, but then I make mistakes. If I copy from the board, from my notes, it's boring. So if I make mistakes, you have to like allow for that a little bit. Okay, and then you can check that these are inverse. These are mutually inverse, and when I did it, I needed, so these are mutually inverse, so that is, you can find the right identifications, okay, to justify that we have an equivalence. And you'll need eta for products, and you'll need eta for pies. Well, for sigma, really, and for pies. So remember, we postulated there's that uncomfortable thing about what exactly should be definitional equality. What I ended up using in the proof is that the pair first m, second m is m. I use that. And I also, that's what I mean by eta for sigma, and the eta for pi is what you think lambda x mx is m, okay, and I use that in my argument. So since these are around definitionally according to the way the book is written, granting that there's some uncertainty about exactly what definitional equality should be, but assuming I gave those as rules, then you can just write them down and it's a little calculation. Okay, so this is in fact an equivalence. Okay, that those two types are equivalent. Okay, that's as it should be. So the idea then is that, remember when we talked about it, is what makes this fly is the proof relevance. You see, because I'm given here. Not only am I given, it's a lot like my search for a zero in a vector example, right? Because I'm given as input to the axiom of choice possibly more than you really think I should give it if I'm going to call it the axiom of choice. Okay, so that's where the terminology comes in. Because I'm giving as input a witness, okay, the y, and a proof, okay, that C holds for that particular witness. And when I pass to here, the choice function is pulled out from here, that's no problem. But moreover, I can produce this by consulting the witness, where I say here, take capital F of x, apply it and look at its second component. So I'm using proof relevance, okay? So proof relevant, I'll write just proof relevance here to stress, okay, what I'm doing, okay? So I'm using proof relevance here because what I'm going to do is I'm going to, that's being exploited. And the same in the other direction, right? I have something over here that is, this is a proof of that C holds for that choice of F that we have over there. So we can say that's the choice function, and the proof that it really works is here. And then I apply that proof. I mean, I really use that, okay, to compute what I need over here. Okay, so these things are, it's so to say it works, or it's a theorem, exactly because, well, one might say, okay, it's a theorem because it isn't the axiom of choice. That's a somewhat jokey way to say it. In other words, it's a theorem because it's not an axiom. Well, that's self-evidently true. But what I mean is, it's not really saying what you might think the axiom of choice actually says. Okay, so that's the point. So what I want to do is I want to compare that to, I'll put it over here, what we'll now call AC minus 1, which is a version of the axiom, well, a version of that statement in which we insert some propositional truncations in order to restrict the information flow that is present in the statement of the theorem without the truncations. I'm going to truncate away some information, and then I'll say, and that is the actual axiom of choice. Okay, so this is what I will do. Let me write this down. So the idea is that we're going to write this as AC minus 1. And it's going to be, in this case, now I have to be careful how I'll write this down. The thing that I need most is, let me just check my notation. That's what I just did. Right, so I need the following thing. So this is the following thing. So if I have this, it gets a little heavy, but we do this. So we have A and U, such that A is a set. So this is what I'm going to do is I'm going to try to say it as close as possible to the axiom of choice with which you're familiar. So I say, if A is a set, and you give me a family of types with the property that for every x in A, each of those types is a set. So now I'm like, that's the quantification prefix. And you give me a relation, which I described there as pi x in A, B arrow U, right, that. But it's going to have the property that for every x in A and every y in B, that instance, C of x, y, is a prop. Okay? So that's where the -1 comes in. So then there's another arrow there. Sorry about that. Okay, so there's another arrow there. And now I want to say what the axiom of choice is. So this is just I'm just rejiggering the prefix, of what we're quantifying over. And then the heart of the matter is going to be written here. Okay. So the heart of the matter is this. It says, if for every x in A being a set, there merely exists, that's the point I was mentioning to you before, a y in B such that C of x, y. Then, so if I put parens in, or let's write it here so that you can see that vividly. So now it's exactly that same issue as I did with the vector search for a zero thing, or sequence search for a zero thing. It's the same issue in that I now wish to suppress explicitly giving you the witness, because if the hypothesis of the theorem demands that you give the witness, then we can just push things around and get the thing at the conclusion. But now you want to say, okay, so what can I get out of that fact? What is the correct expression? Well, then we'll say there merely exists an f, which would be pi x in A, B, such that, and now the same looking thing, pi x in A, C of x, f of x. This is called AC minus 1. And this is not a theorem. This is not going to be something we can prove, okay? And so I'm gonna say something about this. Okay, so let's do that. But first of all, let's look. So this, you might say, expresses the axiom of choice you were thinking of, okay? Because what I'm saying here is, I'm using the truncation to express mere existence. I'm deliberately weakening my hypothesis. So in a certain sense, what happens is the reason the axiom of choice is, an axiom and that one has to think about whether you accept it or not and all that, is because this is kind of expressing the idea that there is a, how would I say it, a scattershot choice that the idea is that whatever x is, there merely exists. I don't know what it is. I'm suppressing the idea of the functional dependency of the witness y on x, because this is a proposition. So any two elements of it are equal, okay? One is as good as any other, okay? So there's some kind of, for lack of a better way to say it, a disconnected choice of y from each x. That is, each choice of x, you somehow or other give me a y, and we don't know anything about how the various y's relate to the various x's, okay? And that because I'm truncating this. If I don't truncate it, then the functorial dependency of y on x is reflected in each choice of x gives me a y, if you suppress for a moment the truncation. And moreover, if I have equal elements here, then they will get equal elements here. But now when I put in the truncation, you still have a functorial dependency, but it's been degenerated because this is now prop. So you're not really saying anything about the witness anymore, okay, because you've squished it all down, okay? You've collapsed it all to a proposition. So you say, if for every x there merely exists a y, then certainly you wouldn't postulate the axiom this way, that there constructively or fully, in a full-throated way, exists an f, okay? But you can say there merely exists one, okay? And that's the idea, that this type is inhabited. That's what would be the claim. That's what you would do. Okay, so this, I claim, is much closer, okay, to expressing what you mean by the axiom of choice. So the nice thing about truncation, and so this particular, since we're only at the level of sets and propositions, this is also expressible in the new Pearl type theory without any problem, and using the squashing. And I mentioned to you that was the motivation, not directly the axiom of choice so much, but that searching example I gave you. And it was the same idea of suppressing the information that goes there. Okay, so this is the statement of the axiom of choice. So one thing, AC minus 1, okay? So the nice thing, first of all, is that, as I repeatedly say when talking about type theory, is you see the constructive setting is more expressive than the classical setting, even though, you know, it looks superficially like I'm depriving you, like Hilbert said, oh, you're depriving a mathematician of a fighter of his boxing gloves, or something like that, if you take away the law of the excluded middle. And that, you know, for all his great genius, I think he was just wrong about that, because I can selectively give the fighter boxing gloves. So I can make distinctions. So here, if I'm in a setting in which, first of all, it just holds as a theorem, I can choose by introducing identifications, which I've done here. I can express the weaker thing that is only expressible in the classical setting, and the classical setting doesn't get to say that at all, okay? It never gets there. So it becomes less expressive, okay? So same thing happens. There are many versions of that phenomenon, and it's worth understanding it because it's like one of the central lessons of type theory, that is the case, you know, and the central lessons of constructivity, in fact, that is the case. So the nice thing is we're able to express that. Okay, so now let's do a little hocus pocus on this to reduce it to something even simpler. There's another way of saying the same thing. And what I'll do is observe that by the very equivalence that I mentioned before, if you look at this one on the right here, sigma f in pi x and AB, such that, as written out here, cxf of x, well, so that thing is equivalent to, what I'll do is I'll run the AC infinity, so to speak, backward, okay? And I'll say that that's equivalent to pi x in A, the truncation of pi x in A, sigma y in B, C of xy. So that's the first observation. So this is equivalent to that because the underlying type are equivalent. And if I truncate equivalent types, I will get equivalent types, okay? It's not too hard, since these are propositions. Showing an equivalence just consists of a biconditional. Show me a map in each direction, because the required commutation conditions are free because you're in a truncated type, which is a proposition. So if you exhibit two things, F composed with G and identity, you've got two things. They're automatically equal because I know it's a proposition, so I don't have to worry about that. So it's very easy to show that those two things are equivalent. So those are equivalent, okay? So that means, now I need to make some space for myself. Okay, so that means so what we have here is that we can restate the axiom of choice, the negative one version of it now, the truncated version, on B, C of xy. We can restate that as this goes to, and now just write the same thing at the bottom, pi x in A, okay, what am I doing? Yeah, sigma y in B, C of xy. Okay, so that's a restated. So AC minus 1 can really be thought of as that, as saying this thing now, modulo. So some version of AC minus 1 consists of composing with the equivalence that I mentioned here. And so we get that. And then just a moment's thought says you can really reduce this to a simpler form, which says, in general, I think in the book it might be called x and y. We have this, let's write it y of x, is equivalent to, or we have a map from here to the truncation pi x in A, y of x. Why? Because suppose this holds, then your x is A and your y is this guy. Okay, this is my guy. And I've written things now so that the truncation of the y is the truncation of the pi of the y. Okay, so this clearly follows from that. And the other way around, if you have this, you can just choose this to be x, choose that to be y, and choose that to be 1. Okay, and if I'm not mistaken, you'll get this as a as a consequence. So this is equivalent, okay? So in fact, I think in the book, this might be the definition, or there's, let's call it prime and double prime, just to be like careful. Okay, so another expression of the axiom of choice in the propositional case is like this, where, okay, this is a set and y of x is a set, okay? Because that's the thing I'm writing down. So it says, you can think of it as, if this is expressing the mere inhabitation of y of x, this says the product of a family of inhabited sets is inhabited. Okay, that's what is being said there, and that should ring some bells. Okay, and that's, there's whole books written on equivalence of the axiom of choice in the conventional set theory. Some of them are quite non-obvious. This one is rather obvious, but there's some non-obvious ways to state the axiom of choice. But anyway, this is one of the many equivalents, okay, of the familiar standard equivalence of the axiom of choice. Okay, so the nice thing anyway that I wanted to say here is that we get to express it, okay, that we can write that thing down. Okay, so now let's do that. Okay, so let me pick up where I am. Yes. Okay, so that's what we've done here. Okay, right. And in fact, the only other thing is in the book, it works out, I won't work it out at the board here, that you can really just state that as an equivalence.
If you want an AC0, say, you would just change his set to his groupoid and bump the truncation up one?
Yeah, I guess that's, I didn't prepare that answer to that question, but I will say probably AC0 will, you would think offhand that certainly the relevant important point here is right there. And I think that's what you might do, but I'd have to actually think, I invariably when I extemporize say the wrong thing. So let me say probably. So now I can't be said to be wrong because I equivocated. So, okay, so that's good. All right, so now the thing that that is also proved in the book that I want to say, and I want to be careful about my time here, is the following thing, is the requirement that this be a set here. Where are we? Over here. So the statement is, so the statement is that what we're doing here, this should really be stated as, if I want to be careful, x in u, I'm putting this in front of it. This goes in front, okay, is set. So just get this right. And I want to know for every y in x arrow u such that, okay, component y's is set y of x. Okay, that's so this arrow, this is the prefix to that condition. So the fact that's in the book, which I will not reproduce here, okay, which you can write down, you can see it in the book, is if x is not constrained to be a set, is not constrained to a set, then the statement is false. That is, it can be refuted. The statement means this version of the axiom of choice, but in which I don't demand, I get rid of that assumption, okay? And how does it do it? Well, by exhibiting something which is a groupoid and it's not a set, and that's worked out in the book. And once again, it uses the same kind of reasoning that I've since erased, having to do with the center of contraction of the sigma, the partial identity type, the contractibility of the partial identity type. Okay, so let me not go through that because I'm budgeting my time here. Okay, so you can see that this is, so there's a discussion in there that shows that this matters. Okay, so that's what we're going to do. So I want to discuss a couple of other things because I want to tie up some loose ends today, and then next week I will start talking about inductive types. That's my plan. Okay, all right, so let me tie up a few loose ends. Okay, so nice thing is that you can actually discuss the axiom of choice. I mean, yeah, you can discuss the axiom of choice quite explicitly in the setting, in the type theoretic setting. You can discuss using the propositional truncation. Okay, so now I want to say something about equivalence. I said I made effectively a typo at the board because I started extemporizing about equivalence last time. So let me mention a few things about equivalence. Okay, so I'm going to go through these very quickly. I'm not going to go through a lot of details. I'm going to give you the rough idea because I think it gets very technical and it probably isn't so much fun to do at the board. But let me give you the highlights of the issue. So we were talking about this idea about the need for a notion of not that f of given f is an equivalence. We want that to be a proposition. That is, that it has at most one proof. Okay, so let me explain that. Okay, so the idea is the following thing. So remember, so we did this. We define what it is to be a or for f, which goes from A to B, to have a quasi-inverse, was just defined to be, well, what you think. There's a G from B to A, which is left and right inverse to it. So we say that, well, a way to say that is F composed with G is homotopic to the identity on B, and G composed with F is homotopic to the identity on A. And remember, the function homotopies mean the universal quantification. So by function extensionality, this could really be replaced by equal signs because we have, in the presence of function extensionality, you can just say F composed with G equals the identity because that exactly, function extensionality says exactly that this is the same thing as that, okay, instantiated here. So that was the notion of a quasi-inverse, okay? So the thing that is developed in the book, and I'll sketch it for you here, is what we're going to do is we're going to show, okay, that the property or the type quasi-inverse of f, which is defined by this, is not necessarily a proposition. A proposition in the technical sense of the meaning proposition. Of course, it's a type, so it's a proposition, but it's not necessarily a prop in the sense of being a -1 type. Okay, that's the key thing that is developed here. So the way it's done is kind of cool to see what's going on here. So what we do is we say, well, the first thing we need is the following fact, which we can write down, which says that if F is such a map, and it has a quasi-inverse, or that is, we have an inhabitant of this. Let me give it a name. So we'll say there is a proof E that F has a quasi-inverse. Then in that situation, we can say that being a quasi-inverse is equivalent to, make sure I get this right, the product of the loops in A. Okay? Because this says for any x in A, let's look at the type of the paths that go from x back to itself. Okay? So this thing is sometimes notated, there's different ways, but the loop space of A at x, like that's one notation I'm pretty sure that you see, which tells you, you're specifying the base point, you know, what you're doing, and you're looking at all of the loops that exist based at that point, which always include the little one, okay, for reflexivity, okay, that we write there. Okay, so that's the idea. And so the idea is that this property of quasi-inverse can be thought of as being that. Okay, so this is the first idea, and I'll explain the proof of that in a minute, but I'd rather give you the high-level thing. Okay, so we can do that. All right, and then there's another fact which there's a proof in the book, but I'm actually gonna, if we have time this semester, I hope we do. There's there are more appealing proofs than the one that occurred. The order of development of ideas in the book made it awkward to do something at a certain point, and so I'll just state it instead as a fact, which is there is a type X such that this product is not a proposition.
I'm confused. How is this first fact true if F doesn't appear on the right?
I actually didn't hear what you said.
This first fact,
Yeah.
Q of F is equivalent to something where F doesn't appear.
Yeah, that's right. That's exactly right. Because, that's exactly right. Yeah, that's exactly right. Well, I have to go through the proof to show you. But the intuition is right. A and B are kind of equivalent. So what do I want to say here is, well, let me remind myself of what the proof is. Okay, we can go through the proof and then we'll see how that comes up. So what will eventually happen here is we're going to say that the data we're given of having being in equivalence will let me get a path in the universe between A and B, and then I'll do a path induction on that path, which I can then, by path induction, assume is reflexivity. And if the path is reflexivity, then by univalence, it's actually represented by the identity equivalence. And then I'll end up considering that the identity equivalence here gives me that. That's the way the argument in the book goes. Pavonia.
We could have two maps from the circle to itself, one of which is the identity, which is clearly an equivalence, and one which just collapses everything down to a one of those is equivalence and one of them is not, but the statement on the right would be the same for either one.
Yeah, so you're saying, well, before I get to that then, you're saying again, so tell me. I believe I'm...
So we've got two maps from the circle to itself.
There are two maps from the circle. So we have F and G, which go from S1 to S1.
One of them is the identity.
Yeah, so let's say we have the identity and we have
F. That just takes everything to the base point.
Okay, so like, K, let's call it for the constant one. Okay, all right.
Now, Q invoke is certainly true. So then
Yes.
IXA x equals x should be true.
Right.
But then Q in K would also be true.
Pavonia is shaking his hand vigorously. Did I state something wrong? Go ahead.
Well, you have the E of the type quasi-inverse in the assumption.
It's hard for me to hear you.
You already know that F is a
Yeah, we already know that F is an equivalence. Okay, oh, maybe that's what the issue is. We already know that F is an equivalence. Okay, so that's the important point. And the argument, I'm slightly worried about time. The argument is, as I said, that the fact that you've got an equivalence will give me a path in the universe, and I'll do path induction on that path, which will then reduce me to reflexivity. And reflexivity in the universe by univalence is always witnessed by the identity. Okay, so this will end up saying that Q inverse of the identity is that, and then we'll be able to prove that the Q inverse of the identity is in fact that, and we'll be done. That's the outline of the proof. Okay, so that's what I wanted to get to. So the point is that you can find an X which is not a prop, and an example of this, which Spencer just provided, is S1. Although I haven't proved this yet. Okay, so I'm going to prove well, actually, what X is going to be is what is called pi 0 of S1, which is the fundamental group of S1. Okay, and so that is not going to be a prop. Okay, because we will eventually be able to show that's Z. Pi 1 of S1 is Z. Okay, that's what I want. Pi 1 of S1 is Z. Okay, so that will be my X, and so this is not a prop. This is a set. Z is the group of integers. Okay, so that is not a set. Another version of it, you can actually go completely crazy. There's a theorem which says you can make this be, what is it called, KG1 or something, KG something. Which is what's called a construction that says I can construct a space whose fundamental group is any group that I want it to be. Okay, and so I can pick that. So I pick for G whatever I like. Maybe I pick it to be Z, and then I will end up constructing the fundamental group, a space whose fundamental group is G. Okay, so that's another possible choice. Okay, that I can have here. Yeah, it's called KG1. Okay, in the notation, so there'll be eventually another one. So that will come up a little bit later. It's more convenient in a sense. Once you have these facts on the board, then it becomes very easy to do the reasoning. So now, okay, so a corollary of this is, okay, so quasi-inverse is equivalent to that, and that's not a prop, then this can't be a prop either. So the corollary is, in general, it's not the case that is prop. It's not this is quasi-inverse of F. Need not be a prop. Okay, so this is how the argument goes. Okay, and I'm suppressing the details. I'm not giving the proof here. I verbally said what the proof looks like here, what I wrote out. Okay, but that's what you do. So the critical thing was characterizing what is the quasi-inverse of f in this manner. And then this is the sort of thing that people have studied a lot, because this is for each x, it's the loop space associated with that. So when you look at the fundamental group like that, that's a truncation of a loop space. And so that's an example we want. Or more generally, what are called the Eilenberg-MacLane spaces, which is this construction that says the space can be as bad as you like, so to speak. I can pick any group I want and make a space that has that as its fundamental group. That's the one part, and so so in other words, it's ridiculously not the case that quasi-inverse is a proposition, because I can go on all day finding spaces that have non-trivial structure. They're not propositions. Okay, so that's the outline of the argument that's in the book, so you can look at that. Okay, I won't reproduce it here. So that leads to the following notions of inverse, and then this will come back to my characterization of contractability a moment ago. So what is a good definition? So what is a good definition? Definition then of is equiv f, that a given f in A arrow B is an equivalence. So what we're arguing is the criterion is it should be a proposition. That is, something should be an equivalence in the sense of is equiv in at most one way, up to higher homotopy. Okay? So quasi-inverse of f doesn't qualify. Okay? That's not a good one. But that's what we're just arguing. But there are three other good ones, and the one I like the most, just like as a personal thing, is the contractability of f. So we will say what is called is contour of f. Well, this is be careful of the overloading of the notation. So I'll define what this is. There's another one called, it's a bi-equivalence, and this is the one we mentioned before, which is you have a left and a right inverse, which are given separately with proofs that they are left and right inverses, so that you have G and an alpha and H and a beta inhabit the bi-equivalence type. So it tells us we have a left inverse G and a right inverse H, and alpha is a witness to that fact and beta is a witness to that fact. So that's one of the definitions. This is momentarily. Okay, and then there's another one which is called is a half adjoint equivalence called F, and look at this. I'm not going to have time, so let's look at this in the book. Okay, you can write it there, which is basically, you can look at it as quasi-inverse plus a coherence condition. And the coherence condition is a commutativity requirement that is reminiscent of the notion of the same notions you get when you have an adjunction. Okay, so that's where it's called half. So this is called half adjoint equivalence. Now, for technical reasons, various ones are useful at various times, but as a matter of like personal preference, which is not worth a lot, but I'll just say, this one feels nice to me, and this one I like, which is Voevodsky's original one, to my knowledge anyway. And I will mention what that is because it ties in with the idea of contractability expressing unique existence. Okay, so what you do is you say, let me find it. Okay, so we say for f in AB, we define a contractible map now, not a contractible space. Contractible map, okay, means that, this is by definition, what are called, it means that all of its fibers are contractible, and we'll see what that means. So that sounds rather abstruse, at least it did to me the first time I heard it. But now we'll see. We'll see why it's not abstruse. Okay, so what is the fiber of f over y? Well, it's the sum of all the x's in A, such that f of x is equal to y. Because we have, sort of A and B, so A and B, and we have f goes down here, takes A to B, right? That's the setup we're in. And if you pick a y down here, okay, then the fiber is that line that I often draw here, which is the fiber of f over y, assuming this is actually sent to y. I mean, pick your y, look at the things that are sent by f to y, and we often draw it that way. It's kind of nice to think of it like that. And if you gave me another y prime over here, there's of course the fiber of f over y prime. And guess what? What should we say immediately about this that would make some sense? Okay, saying something about the fibers. Look at the sum of all the fibers. What do you get? If you have f and you look at the sum of all of the fibers, what should you get? Think of the sum as like the union. I want you to answer me because I want to make sure you're with me. Come on, Evan. So what would you expect to be true? If I look at the sum of all the fibers, right? The sum over y and b of all the fibers of f over y, okay? What do you think that space might be? Well, if these are all the fibers, and f is a function that takes everything in A down here, okay? Then if I sum up all those fibers, I should get A, right? Okay, so check that, all right? So I just do that by way of like, ooh, that was not nice. Okay, so I'm running short on time, so I want to just get to one point, which is to define and discuss the Voevodsky's criterion, which is this one. Okay, so what is this thing saying? Okay, so now what we're going to do is so Voevodsky's criterion for being an equivalence is to say that f is contractible, which is to say that all the fibers are contractible. So can you tell me what that is saying? I just want you to see what is going on here. So let's expand this, right? It's saying for every y and b, something is contractible. That's there exists a unique, right? So this is saying there exists, okay, I don't know, let me make a letter z, okay, which is in the fiber of f over y, such that for every z prime, which is in the fiber of f over y, z is equal to z prime, of course, in the appropriate type. So this is exists unique. Write it closely. So where have you seen this before? Okay, I'm saying something about f, right? So there exists unique. So fiber of f over y says if you pick any y and x, then there really is something. Okay, pick any y here. Any y at all. Pick anyone you like. It will be like a carnival barker. Pick a y, any y. Okay, you pick the y. It claims that there actually exists an element of this fiber, and moreover, all the elements of that fiber are equal. So what is that saying? What's another ordinary way of saying what am I saying about f in very ordinary terms? You probably said it. What did you say?
It's a bijection.
It's a bijection up to homotopy. So what this is saying, and that's what I want you to see, is that f is a bijection up to homotopy. Okay? And of course, I'm selling you a bill of goods. You have to prove everything, but one would think that's a good definition of equivalence of two types, is if I have a bijection between them, where it's the right sort of bijection. That is, it has a functorial behavior, it respects the groupoid structure, and when you go back and forth, they're mutually inverse. That's guaranteed by knowing that wherever f sends something, or you look at anything in B, so we know it's a function this way, and moreover, it has a post-inverse, because if you give me any y in the bottom, which I'm sort of thinking of as a base space at a moment, give me any y down here, then indeed there's exactly one up here. So that's my inverse, okay? And so plausibly, I should be able to get a bi-equivalence, at least, okay, out of this by virtue of the fact that I've said it's a bijection up to homotopy. So the point is the contractability is expressing a unique existence property, and that should harmonize with what you thought a priori. Of course, the devil's in the details. You got to actually work all that out, but that indeed does work. And so this is Voevodsky's definition actually of equivalence, which I wrote here. So this is the one, contractibility of F, which is written out like this: that all of the fibers are contractible, which is exactly saying that F is up to higher homotopy bijection. Okay, that's what's being said. So my point really there is that if you're one of the people like me who was not a priori, had some like multi-year, experience with working with notions like contractibility and so on, then it was a little opaque what was going on there. So I was trying to say, well, if you just unravel what it all means, then you see that that it's expressing something that you might well have expected would be true. Okay? So, all right, so these three things that's shown in the book are all equivalent to each other. So you can pick any of them for my definition of is-equiv. I think the book officially plunks for this one, but anyway, it doesn't matter because all the right relationships are established in the book, so you can look at them. It's very technical. I felt I tried to find a way to express at the board the proofs of all the equivalent, but it seems like it'll be a little dull, so I'm going to let that go. And you can read that. It's in chapter 4, I think it is, of the hot book, and so you can see why these things are all equivalent. And I gave you the outline of the argument as to why this is not a good definition, even though it can be a handy way to show it, because it logically implies any of these. And because you can take this and build a biequivalence out of it, that's the idea. And so that's our definition of equivalence, and then that's such a thing, these will all turn out to be props. All right, so the important thing is that these are all props. I forgot to say that. So that's what the check mark meant, okay, that those are all props. That is, the data that is classified by these types, there's at most one up to higher homotopy, which is not the case here. Okay, so that's the whole idea. Okay, so that's the discussion of that. So good, I wanted to, I glossed over a few things in order to get to this point. So next week I'll start talking about inductive types, okay? And that's kind of fun stuff, so we'll do that. Okay, thanks for your attention.